Higher order functions are a feature of a programming language that allow us to design functions as we should, as I just described, by expressing very general methods of computation. Let me show you what I mean. So what we'd like to do is to generalize patterns by defining functions that take arguments that give us back the specific instances of those patterns. So, as just a general example, let's look at how we compute the area of geometric shapes based on their length. So here are three shapes: square, circle, hexagon. And the relevant length for each is the side length for the square, the radius for the circle, and the side length for the hexagon. And the area of each of these can be expressed simply as r squared pi r squared and 3 square root of 3 over 2 r squared. So what we're going to do is look at these three formulas and find out what they have in common and what makes them specific to a particular shape. So it's these constants, 1, pi, and 3 square root of 3 over 2, that are specific to the shape we're interested in. The rest is just how you compute the area of a shape. So if we find this common structure among similar related problems, we could share the implementation. Alright, let's actually do that. So, here we are. We're going to write some code about generalization. So we can define a function, the area of a square of side length r, by returning r times r. And we can define the area of a circle with radius r as returning r times pi. And what's pi? Well, from math, we can import the constant pi. And then we can come up with the area of a hexagon with side length r, which is r, return r times 3 times the square root of 3 divided by 2. Okay, so now we're in business. We can take the area of a hexagon with side length 10, and it will tell us it's a little bit less than 260. Which is great. It will also tell us that the area of a hexagon with side length negative 10 is the same thing, which is not quite right. So what are we going to do about this? Well, let me show you something. It's called an assert statement. It starts with the keyword assert, and then is followed by an expression, which is a Boolean context. If that expression evaluates to a false value, then an error message is printed to the user whenever they run the Python program. So 3 greater than 2, that should always be true. If it's not, then math is broken somehow. So when this assert statement executes, and this is a true value, then nothing happens. But if I said something that is in fact false is false, then I will get an assertion error and the message that I printed out. So we can put an assert statement in here, assert r is greater than 0, and then a message if that's not true. A length must be positive. Now that fixes the case for area square, and we also need to make sure that r is positive in area circle and r is positive in area hexagon. So I could copy this line and I could paste it in here and I could paste it in here, but then I would be repeating myself, and I'm not supposed to repeat myself. John told me so. Okay, so what do we do about that? Well, we can generalize these three examples by factoring out the part that they have in common, r times r, and also this assert statement that a length must be positive. So we're going to define a function called area, which takes a length, and then it also takes a shape constant that gives us the area of the shape that we're interested in. We're going to assert that the length is positive. And then we're going to return r times the shape constant provided. Now, this function isn't necessarily that intuitive. It certainly requires some documentation, which I'll skip for now. But what it is useful for is for defining all of these area square, area circle, and area hexagon functions that we already have. So, to take advantage of a common implementation, we can just call area with the appropriate shape constant. So finally we have area R, and 3 squared root of 3 over 2. So if I now execute this file and then start an interactive session, I should be able to compute the area of a hexagon with side length 10 and get the same result that I had before. But if I pass in a negative number, well, I'll get an assertion error that a length must be positive. We can also generalize not just over numbers, but over computational processes. So the common structure among functions might not be just a number like we saw with the shape constant. It could be something more complicated. Here are 3 different mathematical equations. One is the formula for summing up natural numbers. So the sum for k equals 1 to 5 of k is shorthand for 1 plus 2 plus 3 plus 4 plus 5, which is 15. And the sum for k equals 1 to 5 of k cubed is a bunch of cubes, 225. And here's the third formula. The sum for k equals 1 to 5 of this expression is these terms, which sum to 3.04. Well, that's interesting. We'll look at this formula with more terms, and we'll see that it eventually converges to the number pi. Okay, so we have 3 formulas. They do seem to share something in common. So they only differ in that this has a k, this has a k cubed, and this has something complicated. Other than that, they're all summing from 1 to 5. So it seems that we have some general computational process going on, and then something specific about it. The thing that's specific about it isn't just a number, it's an expression. Okay, we can write code to generalize this as well. Alright. I don't think we need all this anymore. So, let's write a function sum naturals, which takes in an argument, the number of natural numbers to sum, and it sums the first n natural numbers. So how would we use this? We'd call sum naturals on, for instance, 5, and we'd get back 1 plus 2 plus 3 plus 4 plus 5 is 15. So we can implement this via iteration by writing total and k is 0 and 1, where total is the sum that we're going to return, and k is which natural number we're going to sum next. So, while k is less than or equal to n, the total that we want to, the last number that we want to sum, we are going to rebind the names total and k to total plus k and k plus 1, respectively. And then we will return total. Okay, now I have a function that sums natural numbers. Let's make sure that it works. Yes, it does. Next, we'll write a function that sums cubes. Def sum cubes. Sum the first n cubes of natural numbers. How are we going to call this? Well, it would look like sum cubes, and then I would pass in some number, such as 5, and I would get back 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed is 225. The implementation starts by binding the names total and k to 0 and 1 respectively. And then, while k is less than or equal to n, the last number that we want to sum the cube of, we will rebind the names total and k to total plus the cube of k and k plus 1. and then we return total. See how we did. Okay, so our tests pass, which means some naturals and some cubes do in fact do what we'd like. Notice that there are some similarities between these two implementations. They're basically entirely the same, except for this has a k, and this has a pow k, comma 3, cubing the number k. So maybe we can do better. Maybe we don't have to repeat ourselves. That is in fact the case. Let's start out by defining functions that represent the specific aspects of some naturals versus some cubes. So I'll define a function identity, which takes in a number k and returns it right back. So the expression, which is a function of k that we sum here, is just k itself. Whereas down here, to cube k, we will return k raised to the third power. Now we need to write the generalization over some naturals and some cubes. We do that by writing a function, summation, which takes in the number of natural numbers that we're going to sum over, and we're also going to take in a term, which is a function that tells us how to compute each term of the summation. Okay, so sum the first n terms of a sequence. And how's this going to work? Well, we'll call summation. We'll sum 5 terms. And we have to then pass in how to compute each term. For instance, if we want to cube each term to get 225, we use the name cube, which is bound to a function that raises k to the third power. Alright, for the last time we will repeat this logic in its most general form. So we bind total and k to 0 and 1 respectively. And then while k is less than or equal to n, we rebind total and k to total plus something, and then k plus 1. Now how do we get this something? Well, we have to defer to the particular argument that we passed in, the function that computes terms. So a term needs to be a function that takes in k and returns the term that's the kth term of this sequence. So if we pass in cube, we'll get k cubed, and we pass in identity, we'll just get k. And then finally, we return total. Alright, let's run our doc test and see how we do. So it appears that we've implemented this correctly. So summation 5 cubed gives us back 225. Which means we don't need this implementation at all. We could just return the summation of n with identity. And likewise, we don't need any of this. We just return summation of n with the cube function. And does everything work as it's supposed to work? That's not what I wanted. It certainly does. So it tries to sum cubes, it tries to sum naturals, it runs summation with the cube function, and all tests pass. Ta-da! Alright, let's take a look at actually what happened there. So, we tried to generalize over all of these things. We did it, for example, by defining a cube function, and then defining a general method of computation called summation, which takes in some number of terms to sum, and then a function, which we'll call term, which does the summing. Okay, so this is a function of a single argument. Notice that this function is not called term, it's called cube. It cubes numbers. There is a formal parameter of the summation function that will be bound to the cube function, the function that cubes. So that within the body of summation, we can refer to whatever computes each term. Okay, so a term k, this call expression, actually calls the function that's passed in. And here, in the call expression for summation, do we decide what function to apply to k each time we want to compute a term. So the cube function is passed in as an argument value, and that is a higher order function. It's a function that takes another function as an argument.